Okay, our next talk is by Dmitry Berdinsky, who will be talking about Cayley automatic groups. So go ahead.
Yeah, okay. So thank you very much, Alex, for introduction. So I'm going to present some results about normal forms in Cayley automatic groups. So my talk is based on joint works with these nice people. So Marey, Elder, Prarak, Ruintomia, Jennifer Tabak, and Pong Pitak Tranquil did. Okay, so but before I start, I think I have to recall you a basic concept, a basic classical concept, the definition of automatic group. So it was introduced around 80s by Thurston, Cannon, Epstein, and others. So the idea is that for every group element, you can assign a normal form such that the language of normal forms is regular. And moreover, if you have two neighboring elements in a Cayley graph, then you recognize all such pairs of normal forms by a two-tape synchronous automaton. So let me show you a picture so you can see how it looks like. So here I prefer to think that I have a unique normal form. For every group element, I have a unique normal form. So the picture is like that. So for example, here you have a group element G1, and the normal form is just a string. Right? Well, essentially it's a path. You may think that it is like a path in a Cayley graph. Or you have a group element G2, G3, and etc. Okay, so now suppose that you have two group elements and they are neighboring vertices in a Cayley graph. So then you have two paths, W and W prime. So then this pair, if you write W and W prime one under another, then it should be recognized by a two-tape synchronous automata, right? For every single generator that you have in a generating set. And you have, so I guess you know it very well, you have this famous fellow traveler property, right? So if you move with the same speed along this path W and W prime, then the distance between the travelers will be bounded by some constant. Okay, so this is just to recall your definition of automatic group. And again, so let me emphasize it again. Here, assume that the normal form is unique. I have only one representative for every single group element. Okay, and then around 2011, Kharlampovich, Khoussainov, and Miasnikov, they proposed extension of the notion of automatic groups because the idea was to include some groups, some important groups that are not automatic. And actually what they did, they kept exactly the same computational model, exactly the same. So the computational model exactly the same, but you lose geometric meaning. So let me try to explain the definition. So now, so now again, for every group element, you have a unique representative, right? So for example, for a group element G1, you have W1, for G2, you have W2, and etc. Right? But for example, if you look at W1, it doesn't end up in a group element G1. It can end up anywhere. So anywhere we like, so like, but you keep exactly the same computational model. So for example, if you know that W represents a group element G1 and W prime represents a group element G2, right? So then if you write these two strings representing these two group elements G and G prime, one under another, then it has to be recognized by two-tape synchronous automaton, right? So, and you must have a two-tape synchronous automata for every single generator, right, from your generating set. So that's essentially the difference. And again, the normal form is unique here. So for every group element, you have only one word or only one string representing it. Okay, so and actually this class is I would say it's much wider than a class of automatic groups. For example, it includes all nilpotent groups of nilpotency class 2. It includes all bump-slug solitaire groups. It includes semi-direct product, Zn, Az, and it includes even not finitely presented groups, like, for example, Lamplighter group. So you see that this class of groups is much wider. Okay, so and what we try to do, we try to understand the geometry of normal forms, in Cayley automatic groups, right? So the idea was to look at these distances, at these gaps, because you see in a Cayley automatic group you have this gap, right, between the end of a word representing, for example, G1 and the element G1 itself, right? For example, if your group is automatic, then you can always make this distance to be equal to 0, right? So you can always narrow this gap down to 0. But if your group is Cayley automatic and you keep exactly the same computational model, then you cannot do that, right? So you always have a gap. So now the question is how this gap grows. So at least if you can say something about the growth of this gap, then at least you can say something about the geometry of a particular Cayley automatic representation. So, and what we did, we look at this function. So we look at this function. So now we call it a Cayley distance function. So the idea is that you simply look at all strings. In your normal form, you look at all strings of length less or equal than n, right? And you look at the sizes of all these gaps. So you look at all these distances, right? Between, for example, pi w1 and g1 and pi w2 and g2, and you take the maximum. You simply look at the maximum gap for all strings of size n. So what do you get from this definition? You get a function. You get an, in general, right, you get a non-decreasing function, hn. So now the question, how this function grows? How this function grows? Well, and actually you can also compare this function in coarse sense. Well, here you have a definition which is in fact very close to the classical one you are familiar with. So the first observation that you can make, and it's actually quite easy, you can notice that if this gap is a bounded function, then your group, it must be automatic. So you will not get anything new, right? So your group must be automatic. So this means if you have a Cayley automatic group, which is not automatic, then this Cayley distance function must be always unbounded function, right? So non-decreasing unbounded function. That's what you always get. And you actually can tell much more. So you can look at the lower bound, for this Cayley distance function in coarse sense. So in here we have the following results. But of course, you need to make some assumptions about the growth of den function. So for example, if you assume that your den function is superquadratic, so you can see definition here, right? So then you can construct a function. Well, I don't have a precise construction here, but it is constructed directly from the den function. You have a function phi, which is of course unbounded, such that for any Cayley automatic representation that you have, this Cayley distance function is always bounded from below by this function phi. So this function phi doesn't depend on anything. It doesn't depend on the representation. It doesn't depend on the choice of generators. It depends only on the group. And even more, if your then function is strongly superpolynomial, right? So it's very close, but a little bit different from the classical definition. But anyway, it's very close to it. Then you can say that your function, your Cayley distance function, so these gaps, they are bounded from below by the identity function. So In is just the identity function. So you may think it's like a linear function. So if you don't like identity function, you may think that you have a linear function, right? And these gaps, they are simply bounded from below by a linear function. So this the result that we have for finitely presented groups. And for infinitely presented groups, you can do similar thing. If you, for example, assume that your group is so-called densely generated, so you can look the formal definition here. But for example, if you need to, if you want to think about examples, then all these restricted Riemann products, they give you examples of densely generated, infinitely presented groups. Well, this argument is just a slight modification of a classical result of Baum's law that Riemann products are not finitely presented. So, and if you assume that your group is densely generated, so for example, if you take a Riemann product, then again these gaps are bounded from below by a linear function. If you don't assume that your group is densely generated, you still can bound your Cayley distance function from below by some function which is kind of like a step function, and in fact it's very close to the linear function. But if your group is not densely generated, then in general you cannot say that it is a linear function. You can just say that it's like a step function which looks almost like a linear function. Well, at least in infinitely many points, it behaves like a linear function. Okay, so but you're probably wondering what are examples of Cayley automatic groups, for example, in the class of Riemann products. Well, the only examples that we have are just Riemann products with a virtually infinite cyclic group, and that's it. So if you just take a Cayley automatic group and virtually infinite cyclic, then you always get Cayley automatic. So for all these groups, this Cayley distance function is bounded from below by a linear function. Okay, so and actually we have a conjecture. We have a conjecture that if you take any Cayley automatic group, you have a lower bound. You have a lower bound which is a linear function, but we don't have a proof for this fact yet. So it's just a conjecture. Well, one way to approach this conjecture is to consider, so for Cayley automatic group, you have some kind of fellow traveler property. And actually the results that I showed you before, they partly follow from this kind of weak fellow traveler property in Cayley automatic groups. But anyway, it's definitely not enough to prove this conjecture. So it requires more than just this weakly fellow traveler property. Okay, so what about upper bounds? Well, for upper bounds, things are much easier, right? So what you have to do, if you want to find an upper bound for a Cayley distance function, well, you just propose a certain representation and you try to compute this Cayley distance function. Well, not explicitly, but at least you can write down an upper bound for this Cayley distance function. And that's what we did, for example, for Baum-Slak-Solita group. You can prove that you can find a Cayley automatic representation for which the upper bound is just I. And actually, it follows from the metric estimates that Mare Elder and Jose Burilla proved for Baum-Slak-Solita group. So we couldn't get these results without these metric estimates. Well, and what actually this means? This means that for Baum-Slak-Solita groups, it is sharp, right? So the linear function is the sharp lower bound. That's what we get from this result. And a similar case for the lamplighter group. So it's even easier. You can just construct a Cayley automatic representation for which the Cayley distance function is bounded from above by the linear function. And again, for the lamplighter group, this means that we already know exactly the sharp lower bound. It is the linear function. But for other classes of groups, no, it's not like that. So these things you can get quite easily. That you can prove, for example, that for all nilpotent groups of nilpotency class 2, for UTNZ, for these semi-direct products, the upper bound is exponential. So you can construct a Cayley automatic representations for this group for which this Cayley distance function is bounded by exponential function. But the thing is, you see, there is a huge gap, right? So for these groups, we know that the upper bound, so for some groups, it is I. So for some groups, like for example, high Heisenberg group, we do not even know the upper bound. Sorry, not the upper bound, the lower bound, right? So the best lower bound that we can get here in this family of groups is I, right? So you see there is a huge gap between the linear function and exponential function. So, and we're trying to narrow this gap down, but let's see whether we will succeed. Well, we have a partial result for Heisenberg group. Well, I think you probably don't need to look at this. So I will try to explain the meaning of it. So if you make certain assumptions about Cayley automatic representation of a Heisenberg group, right? So let me try to explain the meaning. So in a Heisenberg group, you have this normal subgroup Z square, right? That naturally sits inside the Heisenberg group. So, and you have these projections, right? So just XY, you project to X, 0 and 0Y, right? So if you assume that these projections are finite automata recognizable, well, roughly speaking, what is written here means this, right? That these projections are finite automata recognizable. Then you can prove that this Cayley distance function is bounded from below by the exponential function. And then what we try to do next, we try to construct a Viet representation for Heisenberg group, for the Heisenberg group. And we could do it for other semi-direct products. Actually, we constructed a whole family of Viet representations for semi-direct products Z2AZ. But this family doesn't include the Heisenberg group. So it was kind of, yeah, it was just an attempt, but it didn't work. So actually, I do not know any Cayley automatic representation for the moment of a Heisenberg group that violates this natural property, right? That these projections are finite automata recognizable. So I still do not know how to construct such weird Cayley automatic representation of the Heisenberg group. Okay, so I have 10 minutes left, so I think I have to switch to another part of my talk. So actually, you can even consider the wider class of groups, not only Cayley automatic, but so-called Cayley position faithful linear computable groups and Cayley polynomial time computable groups. So let me try to explain the idea. Because if you look at the definition of either automatic or Cayley automatic group, right? So you know that you have a two-tape synchronous automaton, right? For every generator, you have a two-type synchronous automaton. So multiplication by generator is recognized by two-tape synchronous automata. And you have a classical result that, for example, you can find in the classical reference Epstein et al. Word processing in group, that in this case, you have a linear time algorithm for multiplication, right? So you have a representative for a group element G. You can get a representative for a group element GA running this linear time algorithm. And actually, you can this algorithm can be implemented on a one-tape Turing machine. So, and there is a classical, well, there is a result, maybe they proved it around 2013. Case Jane, She, and Stefan, they proved that these three things are equivalent. Okay, so multiplication is recognizable by two-tape synchronous automata. It is the same if you say that multiplication can be implemented by a position-faithful Turing machine in linear time. Deterministic or non-deterministic, whatever you like. So these three things are equivalent, right? So, well, what is a position-faithful one-tape Turing machine? It's just a classical Turing machine. The only difference is that you put a restriction that the output must be written starting from the leftmost position. So that's the only assumption that you have to make here. Apart from this, it's just a standard Turing machine. Well, so then what is a Cayley automatic group? So a Cayley automatic group is just a group for which the language of normal forms is regular and multiplication can be implemented by position-faithful Turing machine in linear time. So then how you can extend it? How you can extend the class of Cayley automatic groups? You can simply relax the first assumption that the class of, the language of normal forms is irregular. For example, you may assume that, let's say, it is deterministic context free, for example, right? Or maybe another class of languages. So here we have a definition, right? So here we have a definition. So you see, you assume now that a language of normal forms in a certain class C. If C is a class of regular language, then you get the standard definition of a Cayley automatic group. But still, multiplication, you can do multiplication in linear time. And it appeared that this class is much wider. So for example, it comprises all polycyclic groups, all nilpotent groups, because for Cayley automatic groups, it's still an open question. For example, whether all three-step nilpotent groups are Cayley automatic. Or for example, whether, let's say SL3Z, right? Or SL and Z when N is greater than 2 is Cayley automatic. So there are plenty of open questions like that, right? But you see here, this class is wide. But still, we kept all these basic algorithmic properties. For example, the word you can obtain a normal form of quadratic time, right? So like in the case of automatic groups and Cayley automatic groups, here you can do the same, and the algorithm essentially is essentially the same. And you can go even further, right? So for example, you can assume that multiplication, you can do multiplication in polynomial time. So now you don't need to assume that your Turing machine is position faithful. So this assumption is just irrelevant here. So what assumption? So it might be worth to make the following assumption, that a normal form that you get is so-called quasi-geodesic, because if multiplication is implemented by a position faithful Turing machine in linear time, then the normal form that you get always has is always quasi-geodesic, right? But if it's polynomial, then you don't get that. So this means that it's worth to. So for example, if you study Cayley polynomial time computable representation, it is worth to look at representations that have quasi-geodesic normal forms. Okay, so here some examples. For example, Thompson groups. So it is not known whether Thompson group is even Cayley automatic, but for example, here we prove that it is regular Cayley polynomial time computable with quasi-geodesic normal form. But actually, it follows from the previous result by Mara Elder and Jennifer Tabak. So then the Rith product Z2 with F2, it is deterministic context-free Cayley polynomial time computable. So you can do multiplication in polynomial time, and the form is quasi-geodesic. Well, this group is actually quite bad. So okay, it is regular Cayley polynomial time computable, but I believe that so my conjecture that you cannot construct Cayley polynomial time computable representation with quasi-geodesic normal forms. Well, and here you have this hierarchy of classes of groups. So the class of automatic group is the smallest one here. Then you have Cayley automatic, then Cayley linear time computable, then polynomial time with quasi-geodesic normal forms, then polynomial time computable, and etc. Okay, so what about this?
We have about 2 minutes left.
Yes. So I'm about to finish. Oh, yeah. So what about the Cayley distance function? So can we say anything about the Cayley distance function for this wider class of groups? Well, I would suspect that this question is much harder. So what we have for the moment, we found 2 examples of Cayley automatic groups. So for example, we found a Cayley automatic group. We have an example of a Cayley automatic group for which this Cayley distance function is bounded from below by a linear function. But for the same group, you can construct a Cayley linear time computable representation for which this Cayley distance function is just 0. Well, this is something that you probably can expect, right? Because now you have a more powerful computational model. So this means that you can try to narrow this Cayley distance function down to 0. And we have a similar result, but for regular polynomial time computable group. So we found an example of a group. So in the second case, it was a Baumschlag-Solita group. So for this group, again, the Cayley distance function, if you consider any Cayley automatic representation, then the Cayley distance function is bounded from below by a linear function. But you can construct a regular polynomial time computable representation. So the language of normal forms is regular. Multiplication, you can do multiplication in polynomial time. And this Cayley distance function is 0. So this means that normal forms end up exactly in group elements, like in the case of automatic groups. So for the first theorem, the example was the lamplighter group. So for the lamplighter group, again, it's separated from below by the linear function, but you can construct a linear time computable representation for which this function is just 0. So that's all we have for the moment. And I think the question of low bounds for this wider class of representation is much harder than for Cayley automatic representations. Okay, so here are some questions. We have plenty of questions like that, and this is the conjecture that I mentioned already, right? So we suspect that for all Cayley automatic groups, the lower bound is just linear function, but we don't have a proof for this yet. Okay, so here are some references. So this still a main reference for automatic groups. And this is the main paper for Cayley automatic groups. Actually, the paper where Cayley automatic groups were introduced. So this is the result to KJ and Stefan paper. So sorry, that's the reference to this paper. And well, so my talk was based on this preprints. So yeah, I think I'm done. So do you have any questions?
Okay, let's thank the speaker. Are there any questions?
I actually have a stupid question. I'm just wondering, there's this notion of asynchronously automatic as well. Like, what is the difference between this and KD automatic?
In the case of Cayley automatic, it is synchronous. So automaton must be synchronous. So the computational model is exactly the same as in the case of Cayley automatic. As in the case of automatic group. So the automaton here is let me show it here. It is synchronous, like in the case of automatic group. It's not asynchronous.
Okay.
So yeah.
The Dane function for asynchronous automatic is upper bound quadratic, exponential. So you still don't get lamplighter and things like that.
Yeah, so it's in fact I think it's still open question. I mean the interaction between asynchronous automatic and, for example, Cayley automatic. So you cannot say that, for example, well, so in some sense, Cayley automatic, the class of Cayley automatic groups is wider, right? Because it includes infinitely presented groups, for example. But on the other hand, you might probably find an example of asynchronous automatic group which is not Cayley automatic. So, but that's something that I do not know. Well, actually, there are plenty of open questions. Like you take a group and you ask, is it Cayley automatic or not? And there is no any like result like that saying that a given group is, for example, is not Cayley automatic. Apart from some like simple examples, you just take a group with undecidable word problem. Yes, it's not Cayley automatic, of course. But apart from these things, there are no any results like that saying that a given group is not Cayley automatic. And well, it's still a problem how to approach properly to the class of Cayley automatic groups. But you see, it's wide. It's much wider than the class of automatic groups.
Thank you.
Thank you.
Are there any more questions for the speaker? No. So earlier on, you mentioned that the Cayley distance function for Heisenberg group wasn't known. It was only known that it was bounded between linear and exponential.
Yes, so I can just so for.
But do you have any like intuition about which one it might be closer to, or what it might actually be?
Well, so So for the moment, from the results that I show you, what we have, the lower bound for the Heisenberg group is the square root of, cubic root of n. But I personally believe that it is exponential, but I don't have a proof for this. So I believe that the lower bound is just exponential. So, and you cannot do better than that, but I might be wrong. So actually, this is the problem we're trying to look at now, but so far there are no results yet. So we have to probably look at it from different perspective. Maybe not from the perspective on the then function or things like that. So yeah, so you see, the gap is just huge. What we have, yes, you can easily construct a Cayley automatic representation of a Heisenberg group for which this Cayley distance function is exponential. And this is the lower bound that we have. And you see the gap is just, it's big, right? And I believe that the lower bound is exponential, but I might be wrong. So might be totally wrong.
Thank you. Thank you.
Thank you, Alex, for your question.
Are there any more questions? Okay, if not, I'll end it now.